Engineering, science, electrical. As you're now fully aware, the module's kind of split in half. Half of it's taught by me, electrical half, and half's taught by Adrian, mechanical half. All right. This is the first time Adrian's taught that module as well. Okay. So, what we're going to do in this lesson, there's two learning outcomes. One mechanical one that Adrian will have introduced you to, or will introduce you to this afternoon, and there's an electrical one, learn outcome 2, investigate and apply direct current and alternating current theory to electrical circuits. So there's a fairly broad spectrum of things I could do in there. It's not too prescriptive. So the assessment of it is a practical investigation lab report worth 20% of your overall mark, and an examination worth 30% of the overall mark. 1 hour exam on the electrical side, and then you'll have a similar thing, an assignment and an exam worth the other 50% for Adrian. Okay, so that's how we assess this module. So straight in there, we're going to go back a little bit too and go over some bits that you would have learned, certainly if you did BTEC here or anywhere else. Electrical principles. Voltage. Voltage is the pressure applied to a circuit. You can think of it as the force that pushes the current around the circuit. There's almost an analogy with water there, that you've got a pressure from water being high up in a tank, and if you let it go, that's a force that will push it down to the bottom. So your battery or your mains electricity is the force that pushes the current. Measured, it has the symbol V. It's measured in volts. Okay, can also be found to be given these names: potential difference. Difference in voltage between 2 points. Yeah, sort of, but I'm not going through every detail that's in the book. I'd rather you concentrated on following what I'm talking about and asking questions than trying to match what I'm doing here with what's in the book. All right, you can use that as help. Potential difference. So if we, and another term, electromotive force, E, often a symbol used, E, electromotive force. It is standard to say that sources are often designated E instead of V, electromotive force, whereas we talk about the volt drop across that resistor, or the potential difference between that point and that point in the circuit. All measured in volts, but different terms. Don't blame me, I didn't make them up, and I will switch around between them because you're going to see different terms in books. If you get two different books, one will talk about voltage, V for the V battery or something, and other books will have E for sources. So you need to get kind of used to that. The Germans use U to denote a source, probably because that's how they fit in their language. If you work on any German machines, you'll come across US for the supply voltage and so on. No one particular book. All right? No, there isn't. The key point here is that current flows in a circuit or component. Current flows in a circuit or component because of a difference in the applied voltage at either end of that component. Okay, so if we have a component in the form of a resistor, and that terminal is made plus 12 volts, and that terminal is made plus 12 volts, no current will flow through that resistor because there's no difference. Yeah. If we make this terminal 0 volts or anything lower than that, current will flow that way. And I'll avoid putting that arrow there. Current will flow that way like that. Okay? If we make that one lower than that one, current will go in the opposite direction. Okay? But if there's no difference, no current will flow. And I am very particular, right? Volts never go through things. If I hear anybody say there's 12 volts going through that resistor, I'll pick them up on it. Volts are across, current goes through. Okay, and very much, there's a lot of maths in this module, but if you understand the underlying electrical principles of what makes current flow, what stops current from flowing, and so on, the maths becomes much easier. Alright? So no potential difference, no difference in voltage, no current flow in the circuit. Everybody happy with that? And have you got your notes you want from it? Current. Current is a measure of the rate at which charge is flowing in a circuit. And is designated by the symbol I for current. So we talk about I1, I2 and I3 and so on. And it's measured in amperes. Another point to note is we're in a scientific module now, not a maths module. I will be even hotter on the fact that you must include units where appropriate in the answers to your questions, and will be marked down for not including them. Okay, that might be where you lose 1 mark, you never know. Okay, the resistance of an electrical circuit, what that is a measure of the opposition or restriction to the current flow. More resistance, less current, less resistance, more current. What law am I talking about there? Ohm's law, yes. Ohm's law will tell you that. If you can remember that, helps you with the Ohm's law formula. If I put more resistance in, I'm going to get less current for a given voltage. Less resistance, more current for a given voltage. You've got Ohm's law without even having to remember it. And you are expected to remember Ohm's law, by the way. Designated by the symbol R, measured in ohms. I won't cause too much confusion now, but you're going to come across some more terms that are measured in ohms. One of them is the impedance Z in ohms. You can think of impedance as AC resistance. And more about that a little later in the module. Okay? When we look at AC circuits. So when a current flows through a resistance in its most basic form, to have some kind of resistance in the circuit, we have to have a load to get that energy conversion into heat, light, or whatever we're looking for. All parts of a circuit have some resistance to flow. Without it, there will be no conversion or use of electrical energy into another form. So the circuit with no resistance doesn't exist. Okay? You're all happy with that so far? So there it is. Numero uno, most important thing in electrical science, Ohm's law. Defines the relationship between the applied voltage, resistance of a circuit, and the current that flows in it. Really, current, I like to think of it as Ohm's law defined in its current form, because current is dependent on the other two things. You apply a voltage to a given resistance, and the current happens in most cases. Yeah, but then the idea of this is we can rearrange it into the voltage in the circuit is equal to the current times the resistance, or we could rearrange it into the form of the resistance is equal to the voltage divided by current. So by a rearrangement we can use Ohm's law. If we know any two of I, V and R, we can find a third one. Yep. And so we'll be having a look. It's applied in many principles of electrical engineering. You will need to remember it. Even when we get further down the road and look at quite complex, even at level 6, Ohm's law still applies, and you can always prove it. Yeah. The second thing goes alongside Ohm's law is the power formula. Power is what it is a measure of the rate at which energy, and energy is measured in joules, is used. In electrical terms, it's the rate at which electrical energy is converted into some other form. Power has a symbol P. We talk about it. It's measured in watts, which uses the symbol capital W. And the power dissipated in a component can be found using the formula P is equal to I times V. Yeah. And then, if you two other formulae for power that you'll also need to commit to memory. And they are that the power is equal to I squared times R. And also you can get power from V squared divided by R. And with those four formulae, that's the Ohm's law one, and that one, if you know any two of the four values, V, I, P and R, you can find the missing two. Yep. Just pick the right formula and use it. Okay? And in fact, all apart from one combination, you could find by doing two calculations of P, I, V and Ohm's law. But you need this one in certain cases. Alright? And they're all rearrangeable, and you can move them around so that you can calculate the bits that are missing. So let's have a look at an example. A voltage of 75 volts is applied to a resistor, and the current flowing is measured to be 15 amps. So here's our voltage supply. Always worthwhile drawing a diagram. 75 volts applied to a resistor, and that resistor is unknown, so we'll give it the symbol R. We'll call that E for the supply voltage. It's a form of electromotive force, and we know that a current is flowing in a circuit, I. And I is equal to 15 amps. Find the value of the resistor. Fairly easy, or probably do the maths in your head. But what formula have we got to use? Yeah, the formula is R, yeah, Ohm's law, V over I, (75) over 15 is 5 ohms. Yep. You're probably not going to get one as easy as that in the exam, but you know, that's the kind of thing you're showing you know what you're doing by writing the formula out, putting the numbers in, giving me an answer with the units. So starting from day one, I'm going to show you what I'm expecting you to do in the exam questions. Alright? What for that? Oh, that'll be out of 100 like any other exam, and then I think it's 100. I can't remember. I have to have a look at last year's paper. The number don't really matter. That's what percentage you get, Dom. I think so. I can't remember. I have to get last year's paper out and look what it is. Oh yeah. Right. Another example problem. Have a go at this one on your own. Find the voltage required to be applied to a circuit with resistance 16 ohms to make a current of 1.5 amps flow through the circuit. Also calculate the power dissipated in a resistor. So I'm asking you to find V and R. Where are we going to start with this problem then? Yeah, tell me then, Lewis. IR. You okay with me using the dot notation for multiplication? Yeah, I hope so. Tough if not. 1.5. When the numbers go in, please put the proper multiplication symbol in. Otherwise that look like 1.5.16. And the answer to that is 24 volts. Yep. Next bit. You knew I was got to say that, Dom, didn't you? Huh? Boom. So you could, in this case, right? In this case, 1.5 times 24 is 36 watts. Okay. In this particular case, you haven't introduced any error, right? But if this first calculation ended up with a fractional value, particularly a third or a sixth, where they're repeating decimals, you're going to round it, and then you've applied that rounded value to the second equation. You may then compound error. So, as a general rule, use what you've been given. So what other formula could I use to find the power using those two values? Yeah, P is equal to I squared times R. And if you did that, you'd find that you get the same result. Okay? So, generally, I'd recommend that you, at first point of call, is use what you've been given. Obviously, if you still can't get to the answer, you have to use a calculated value. Include as much accuracy as possible. If it is a sixth or a third, put the fractional value in your calculator and only round when you get to the final end bit. Again, same rules apply. Don't evaluate pi until you have to, when that crops up a bit later on in science. On the bottom there, important note. It's important to include the units after any result, otherwise your answer is just any old number. Okay? Sometimes there's an occasion where the answer to a question is a ratio and it doesn't have any units. If there's meant to be units, you should include them. Also, you should include the formula used and your working, because this is likely to gain you some marks if your answer is at the end point incorrect. You'll get some marks for the bits that you did do right. Okay? Any questions? Next bit. Units, multiples and submultiples. We come across the use of a lot of these in electrical engineering. We want to talk about very high values, typically resistance, watts and volts. Sometimes we go up to kilovolts. Ohms, we could well talk about mega ohms. The only one you would normally get anywhere near on giga would be frequency, gigahertz, and even then the subject matter of this course doesn't have us very often talking about frequencies as high as that. Computer engineering, yes, but what you have to be careful with computer engineering is when they talk about kilobytes, they use a capital K because it isn't 1,000. That's 1,024. Yeah, it's 2 to the power or something. I can't remember what it is, right? But mega in computer terms isn't a million. That's 1.2 something million, I believe. Okay, 2 to the power 10 is killer. All right, so you just need to be careful there. We should be using a lowercase k for killer. So if we talk about kilowatts, a lowercase k, uppercase W. All right. But the most important reason for talking about this is if you're using Ohm's law, power formulas, all your units must either be in the base unit of amps, ohms, watts, or volts, or they're all in the same multiple, so they're all kilo, all milli, or we use power 10 notation to denote milliamps, kilovolts, and so on. And there's arguments in certain situations to use different ways of doing it. Okay? But we've got lower values, milli, current, often talk about milliamps, thousandth of an amp, micro, a millionth, farads, capacitance, microfarads, probably the biggest capacitors are measured in microfarads, because 1 farad is a really big unit. Nano, dividing by 1,000 million, and pico, dividing by 1,000 million, 10 to the minus 12. All right. So if you've got a mixture in your circuit, you've got kilovolts and amps. The best way to deal with that is to put them in as the kilo one in as times 10 to the 3. Right? We'll be looking at some problems that will involve that later on. I'm sure you'll come across that before. Each of those have a multiplier to a power, and they step up and down in threes because it's always division or multiplication of 1,000. Series resistance. Oh, hang on, I think there's some. Just pause that.